Okay, what we're going to talk about now is, if you notice, we kind of switched from taking derivatives to doing integrals, and what the following theorem is going to do is going to link that even further. So it links differential calculus, which deals with derivatives, to integral calculus. Okay, and first we'll start with a continuous function on the closed interval AB. Then if f is continuous on AB, then f is continuous on AX, and x is less than or equal to b. So x is a variable, so we're going to switch and make this not a constant. If f is a continuous function on AB, then the integral of f of t dt equals a number. Okay, we've seen that. When we take the integral, we get a number. Well, when we go from a to x, we get a function. Okay, because x changes. So let's draw a picture of that. Say, again, if f is continuous, then we can do this in terms of area. Or f is positive, and it's above the x-axis. Just so you see, it holds true for any function, any continuous function. But if we go from a to b, then the integral of f of t dt is equal to the area under that curve, okay, which is a number. But suppose we go from a, okay, here's b, to some x, and x can be anything. We can move it around. It still represents an area, but the area varies. So the area is a function of x. It depends on x, so we're going to call this f of x. Because every time you choose a different x, you get a different area. So if f of x is equal to the integral from a to x, f of t dt, then f of a goes from a to a. Well, if you're not moving, you're just staying at the same place, then there's no area, so that's 0. There's no area. And let me go up here and put some properties in that we need to talk about. There's two properties, and anytime you go from the same thing to the same number, that's going to be 0. And they're going to kind of cancel. You're not moving, you're just staying in A. And if you want to change the order of the upper and lower limits, then you have to add a negative in front. So instead of going from A to B, we're going from B to A, then that becomes negative. Alright. So, for example, let's try a specific case that we can see a picture of. And my example is f of t is t squared. So we know that's a parabola, and we're going to start this at 0 and go to x. And this is t squared. So f of x is the integral 0 to x t squared dt, which if we do Riemann sums, it's the limit as n goes to infinity, I equal 1 to n, f of xi delta x. So let's use the right-hand endpoint. First off, delta x is going to be x minus 0 because this is from 0 to x. Now x is still a variable, so that's x over n. And in our case, we're going to start it at 0. So we move over by x over n each time. Then the ith interval is going to be ix over n. We use right-hand endpoints. So let's just go from the summation point. I equal 1 to n f of ix over n, and delta x is x over n. That's going to be x over n. Well, our function is t squared, so we're just going to square we get x cubed over n cubed I squared. Using the formula for I squared, that's going to be n plus 1, 2n plus 1 over 6. Okay, and that's going to be x cubed over 6, and all this over n cubed, and that's going to be n 2n cubed. When I multiply that out, you're going to get this, plus something n squared, plus something n, plus another constant. And if you want to FOIL all this out, you can. It doesn't matter, though, because when you divide it by n cubed, you're going to get x cubed over 6 times 2 plus something over n plus something over n squared plus k, some constant over n cubed. And we take the limit of that. The x cubed over 6 can come out front. That's going to be 2. That's going to go to 0. That's going to go to 0. That's going to go to 0. So when all those go to 0, that's just going to be 2 over 6 is x cubed over 3. And that's going to be our f of x. And when we take the derivative of f from, what's the derivative? We get x squared, which is little f of x. So what this showed us was that the derivative of f of x, which is the derivative of the integral of little f of x, is f of x. So we're saying f of x is an antiderivative of f of x. So that statement, this statement right here, is the fundamental theorem of calculus. It relates a derivative and an integral. And it's the first one. There's really two of them. Okay, so let's throw in an example. If I want the derivative of the integral from pi x sine t square root of t squared dt, and it's just like the derivative and the integral undo each other. They're inverse operations. Notice it doesn't matter where it starts. I can start anywhere. That's just a constant. And all this says is that that's going to be f of x. This is our f of t. So f of x is going to be sine x over square root of x plus 1. So it's like saying the derivative and the integral cancel each other out, and you just evaluate the function at x. Now, it's different, though, if it's not x. Okay, again, you can start anywhere. So suppose we're integrating to x squared plus 2x. So we have to remember the chain rule. D dx times let's just say this. D dx is d du times du dx. Because you can think of those as canceling each other out. So if u in this problem equals x squared plus 2x, then we have d dx of 2u t cubed plus 1 dt. That's going to be d du of 2u t cubed plus 1 dt times du dx. Now, it's like these cancel out because they're both u. It's the derivative with respect to u, and you're integrating the u. So you just substitute u in, but then you have to come back and take the derivative of u, which we'll just say is u prime. So going back to x is now u is the same as x squared plus 2x cubed plus 1, then times the derivative of u. And that's our final answer. So the point is, what you're going to do is you're going to substitute in your upper limit. If it's a variable, you're going to substitute that in and then multiply it by u prime. So don't forget to take the derivative there. Okay. Okay, let's look at the fundamental theorem part 2. This is the one that we really use. So f is a continuous function on AB, and let g be a function where the derivative is equal to x for all x in that closed interval. Then you can say the integral from a to b f of x is g of b minus g of a. Now, when you have upper limits like this, this is called a definite integral from a to b. So this is a way to evaluate our integrals. Okay, so let's talk about this. G is an antiderivative of f since g prime equals f, and so is f of x, which we said before, since f prime of x is f of x, where f of x is the integral a to x f of t dt. So g of x is equal to f of x. The antiderivatives are equal, but they may differ by constants. So you have to remember that antiderivatives differ by constants, or may differ by constants. Because when you take the derivative of a constant, it's 0. So this is saying that g prime equals f prime. So g of x is the integral from a to x f of t dt plus that constant. Now g of b is a to b f of t dt plus the constant, and g of a is a to a f of t dt plus the constant. But when you go from the same number to the same number, that's 0, so that's just the constant. What do you get when you subtract those two? So we get the integral from a to b f of t dt is g of b minus g of a, where g is an antiderivative of that. So this gives us a way of evaluating definite integrals. Okay, so let's do an example. If you want the integral, say 1 to 3 x squared dx, then we know an antiderivative of x squared is x cubed over 3. We proved that using the Riemann sums in this discussion in this lecture previously, or you can just use the rule x to the n dx is x to the n plus 1 over n plus 1 plus c. Okay, so what we do is take the antiderivative and we evaluate it from 1 to 3. Okay, so you always do the upper limit first, so that's going to be 3 cubed over 3. Then you do the lower limit, 1 cubed over 3. 27 thirds minus 1 third is 26 thirds. So this is g of 3 minus g of 1. And we write that with the straight line. That straight line means evaluate. So first you evaluate it with the top number, and then you use the bottom number. Okay, look at some of the example homework problems.